Gnanam paramam dhyayam. Knowledge is supreme.
Hello. Now we come to the study of normal field extensions. So normal extensions we want to study. And the very name here, normal, we will show that this will correspond to the normal subgroups. That is why actually the normal extensions came first and normal subgroups came later. So this should be studied earlier. Anyway, but the group theory developed much later than the field extensions. For example, that was because of Galois essentially, who realized that studying field extensions and studying their Galois groups together is a very useful thing, and this has led to many solutions of difficult problems. Alright, so we have a field extension. So L over K field extension. Now I am not assuming that it is finite extension, but I am assuming that it is algebraic. Normal field extension and assume that it is algebraic. May not be finite. For example, the algebraic closure. So I have not come to the algebraic closure yet, but after this I will come to algebraic closure. So algebraic extension may not be finite. Okay. So I will say that definition L over K is called normal if every irreducible polynomial in Kx which has a 0 in L splits into linear factors in Lx. So let me write this in symbols. So what do I say? If I have an irreducible polynomial pi in Kx, irreducible, when I say irreducible over K, if there is x, small x in L with pi of x is 0, that means pi has a 0x in L. So if then all zeros of pi, they are contained in L. This is the set of all zeros in the closure, in the bigger field. All of them should lie in L. That means this pi splits actually into linear factors in Lx. Then your field extension is called normal. For example, so let me give you examples immediately. So for example, if the degree L over K is 2, then it is always normal. Then L over K is normal. Proof. So what do we have to prove? We have to prove that every irreducible polynomial which has a 0 in L, that has a 0 in that splits into linear factors in L. So let pi be irreducible, and suppose irreducible over k, and if x is a 0 of pi and x belongs to L, then because x is a 0 of pi x is 0 and pi is irreducible, this pi must be the minimal polynomial of x over k, and therefore the degree of, because this degree is 2, so since L over k is bigger equal to kx over k, this is the degree of mu x, which is degree of pi. So pi has to have degree bounded by 2. So either pi is linear, in that case we have nothing to prove, or pi is quadratic. So pi linear, then pi must be equal to capital X minus x, which is already done. Otherwise, the degree of pi is 2. Then I know, if I know one 0, I know the other 0 by the quadratic equation formula. So then I know the zeros of pi are precisely, so pi will be then pi x minus times x minus y, and this factor is in L, and this is in kx, which is contained in Lx. Therefore, the other factor also has to be in Lx. So that implies, both this thing implies this factor also is in Lx. So therefore, pi factors into linear factors in Lx. So that means the degree 2 extensions are always normal, and this statement corresponds in a group theory. Every subgroup of index 2 is normal. Okay, so this is one example at least. Now I should tell you also example of a field extension which is not normal. So 2. Now let us take, remember we have given a field, so take any positive rational number q, a in q, which is square free, a is square free, and we are considering this field a positive, and we are considering cube root of a, real cube root of a. So these are denote is, this is in a, in real number. So this is omega, this is omega. Now this field extension, and we are considering this field extension, this one. Now this field extension, the degree is, degree of this field extension is 3. So this is q omega over q, this degree is 3. In fact, this is simple, so this should be the degree of the minimal polynomial of omega over q, but the minimal polynomial of omega over q is nothing but x cube minus a, and we need this irreducibility, therefore we have put this condition square free, and this is 3. So this field extension has degree 3, and I want to claim it is not normal. That means what? I should give you a polynomial which is irreducible over q. It has a root in this, but not other roots are there. But well, this is the irreducible polynomial in qx. it has one root here, but the other roots are the complex roots. Other roots are the roots of mu omega q are precisely that omega and then zeta omega and zeta square omega, where zeta is a primitive cube root of 1. These are the roots, and this is zeta is complex. In fact, zeta is e power 2 pi I by 3. So this is complex non-real root. Therefore, this is real, and this is non-real. This is also non-real. So it has only one root, and the remaining roots are not there. Therefore, it is not normal. So what we checked is q omega over q is not normal. And if you remember, we have seen also this is not a Galois extension. Q omega over q is not Galois extension. In fact, in this case, we know the Galois group of q omega over q. This is trivial, only identity, and the degree is 3. So the cardinality of this group, which is trivial group, cardinality of this group is 1, and the degree of the extension is 3. So therefore it is not Galois. So this is not normal, therefore. So we can have many more examples like that, and we need to characterize this. So this definition is not suitable for deciding whether a given finite field extension is Galois or not. So we are always looking for equivalent definitions. So that means we are looking for theorems which say that the statements are equivalent. So that is what I am going to state now. Theorem. This is a characterization of normal extensions. So theorem. Let L over k be an algebraic extension. And let E be an algebraically closed field. Remember, we have defined what is an algebraically closed field. Algebraically closed field means the only irreducible polynomials are linear, or equivalently there is no proper algebraic extension of that field. These are equivalent, and soon we will prove that the field of complex numbers is algebraically closed, and also we will prove that how do we extend a given field to an algebraically closed field. That will be called algebraic closure of a field. So these things soon we will prove that, but right now I need only algebraically closed field. That means the only polynomials which are irreducible in that polynomial ring over that field are linear ones. Okay, then the following are equivalent. So 1, every k embedding sigma from L to E maps L into L. So that is sigma of L is contained in L. 2 L over K is normal. 3 capital L is a splitting field of some set of polynomials in Kx. So, the last statement here, that means I have a subset of polynomials in Kx, so that if I take all zeros of, so let me recall this precisely, that will help in the proof also. So, what is the last statement? That means the following. So, suppose I have a subset S of the polynomial ring. These are polynomials. This S may be finite, may not be finite. This is a subset of polynomials. So to each polynomial, so I will write this as F S, as S varies in S. This is my indexing set. So indexing set is, so let us call it I in I. There are many polynomials. I may not be a finite set. I is any set. Then to each polynomial Fi, I have their zeros, f of v of Fi. This is a zero set of Fi in a bigger field. So this is finite set. So this set is a finite set. This is a finite set. So I take all of them and adjoin to L. So I take adjoin to K. See, the zero set may not be in K. So it may be in the larger field. This is in a larger field EI. So I take all of them and then adjoin it to K. So K adjoin all VFIs, union I in I. This is precisely what one means by the splitting field. Is a splitting field of the set S. This is the smallest field where all the zeros of all the polynomials lie in that field. This is what one means by this L. So the assertion 3 says there exists a subset S of the polynomials such that L equal to K adjoin all zeros of all F in S. That is called the splitting field of this one. So that is the statement 3. This is because I am not assuming that L over K is finite. If I would have assumed that L over K is finite, then S finite or even one polynomial will be enough. But I am not assuming that L over K is a finite extension. Therefore, one has to consider arbitrary subset of polynomials. Now, let us prove that these statements are equivalent. So, proof. We are going to prove 1 implies 2 implies 3 implies 1. This is what will complete their proof of the equivalence. Okay. Alright, so what do you have to prove? I have to show you the statement. So we are proving 1, every K embedding maps L inside L. This is what given to us, and this L over K is normal. We want to prove it is normal. Normal means if an irreducible polynomial has 1 0 in L, then it splits into linear factors over L. This is what normal means. Alright, so we have to, I am proving this. So let f is a polynomial in Kx, irreducible, and suppose A in capital L, which is a 0 of f. So that is f of A is 0. Then I want to prove that f splits into linear factors in Lx. That means it's normal. That's what I want to check. So, alright, now I want to say that all the zeros lie in L. So to show that V of f is contained in L. So these are all zeros. So take any B. I want to show B is in. So to show B belongs to L. All right. So now, okay, now look at B. So E is algebraically closed field. E is algebraically closed field, and which contains K, and this is B is a 0 of, so Fx is here, so this is algebraically closed. Therefore, remember the last one, so that is, so this B is a 0 of, okay. So note that if I look at the simple extension Ka and Kb, they are isomorphic as K algebras, because they are roots of the same irreducible polynomial. First of all, because this is irreducible, this f has to be mu a k, which is also equal to mu b k, and this is isomorphic to kx modulo mu x mu a k. This is isomorphic to kx modulo mu b k, but this mu b and mu, they are equal, so these are equal. So therefore these are isomorphic, these are actually equal, these are isomorphic, therefore these are isomorphic. So they are, as K algebra, they are isomorphic. Therefore we have an extension. So this shows that we have an extension L. So L is here, L to E. I say there is an embedding here because this I am extending to, see, K is here, K is here, this is contained, and I have, so E is algebraically closed, so E is here. So I use the last theorem to extend this to here. This is an extension of this. So this is K embedding. But then this should map by one assumption is this sigma. Let us call this as sigma. Sigma maps L inside L. But this sigma, this is an extension of this. So we have an embedding. This embedding I have extended from here. Here, this is A goes to B. this is KB, and this is contained here, and therefore I have extended here. So this K embedding should map because of the given condition 1. So this is by 1. So in particular B, which is sigma A belongs to A, but sigma A is B. So I have proved that every root B contained in L. Therefore this proves that V of F is contained in L. So that is L over K is normal. That proves 1 implies 2. So 1 implies 2 we have proved. Okay, now 2 implies 3. We have given that given L over K is normal. And what do I want to prove? I want to prove that, I will show you this, and I want to prove that L is a splitting field of some set of polynomials in Kx. So I have to tell which set I can take. So look at the set S. This is, look at all minimal polynomials of elements A in L. This is a subset of Kx. So take any element in L and look at minimal polynomial and collect all these polynomials and look at that set. And obviously this set, I want to show that this L is a splitting field. That means what? I should check that. So I should check that. So we need to prove the following. So we need to prove that L is precisely equal to K adjoined with all the unions of the zero sets of the polynomials that we are considering as A varying in L. This is what we want to prove. Yeah. This is what we want to prove. Obviously, all elements of L are here, so this is clearly contained. This is clear. Conversely, I want to prove that any element here is an element in L. So because K is contained here, it's enough to prove that the union A in L, V mu A K, this is contained in L. That means, and to check that, enough to prove that each element in this union is contained there. V mu A K is contained in L for every A in L. So that means every other 0 of the minimal polynomial of A over K is contained in L. So let B be a 0 of minimal polynomial of A. Then to prove B belongs to. So to prove B belongs to L. But this B is a 0 of minimal polynomial. This 0 and 1 0 A which already lie in L. So by definition, by condition of 2 says normal. Normal means if an irreducible polynomial has 1 0 in L, then every other 0 is also in L. So 1 0 A is in L, therefore the other 0 B is also in L. This is clear. Therefore we have proved that this inclusion is clear, and once you have proved the inclusion is there, the union is there, and once union is there, K, the smallest field which contain all these guys, they are also contained there. Therefore 2 implies 3 is proved. Now only one left, 3 implies 1. So 1 implies 2 implies 3. These already we have proved these implications, and now we want to prove 3 implies 1. This is what we want to prove. And what is 3? 3 is L is a splitting field. This is 3. L is a splitting field of some subset F of polynomials with coefficients in k, that is the condition 3, and condition 1 is every k embedding sigma from L to an algebraically closed field, E algebraically closed, maps L into L, that is sigma of L is contained in L. This is what condition 1 is. So, now we want to prove that 3 implies 1. So, that means we have given that L is a splitting field of some subset f of the polynomials with coefficients in k. So, let us consider all zeros of all polynomials in the field E is algebraically closed field that was given, and where f is varying in the given subset f. And now you take V to be their union, V E f, f varies in f. Then we have what we have given is L is nothing but the splitting field of this set f, which is nothing but k adjoined with the set V. So, it is the smallest field, subfield of E, which contains all these zeros of all the polynomials. And now we want to prove that if we have an embedding sigma, so let sigma be an embedding from L to E, k embedding. Any embedding, and then we want to prove that. So, to prove sigma of L is contained in L, this is what we want to prove. But to prove that, it is enough to prove that sigma of this means, so that is sigma of kV is contained in kV. But for this, it is enough to prove that sigma of V is contained in V. But for this, because V is a union, enough to prove, again it is enough to prove that sigma of V of f, zeros are in E, is contained in VEF for all f in F, because V is a union of all these things. V is a union of this, but this is immediate from the observation we have been using in this course quite often, namely if x is a 0, if x is in E and f of x is 0, that means it is an element here, x is an element here. Then what is sigma of that? Sigma of x is also 0 of f. This is immediate because f of sigma x, sigma is an embedding, so and f is a polynomial, so this is same thing as sigma of fx, but fx is 0, so sigma 0, which is 0. Therefore, if x is a 0 of f, then sigma x is also 0 of f, that precisely means this inclusion. So, that proves this inclusion, and therefore, that proves sigma of V is contained in V. Therefore, that proves that if I take any element of L, then it is a combination with the elements in V, and therefore sigma of V will be contained in L. So that was what we wanted to prove, that is precisely 1. So with this it finishes the proof of this theorem. Okay, with this we have finished the proof of the characterization of normal field extensions, and we will continue this study further in the next lecture. Thank you.